Hello, good evening. Hello, am I audible? Hello, can anyone please confirm if I am I audible? Niranjan or Vaishnavi? Hello.
Hello. Hello.
Okay. Okay, so I think I am audible. So welcome again. I think now we can start our session. And this is our second session for this NPTEL course, Applied Computational Fluid Dynamics. Okay. This session is based on the content of week 2. And in week 2, we have covered the forms of compressible Navier-Stokes equations and something related to thermodynamic concepts, right? So we will try to solve some problems based on the content of week 2. Okay. And other than that, if you have any query, any question from week 1 or week 2 or any other doubt related to this course, then you are always welcome to put forward. Okay. Well, before starting again, I will go through this map. There are three main steps in CFD, pre-processing. And in solver, we have to solve some equations, governing equations of fluid mechanics. These equations can be mass conservation, momentum conservation, energy conservation, or any other transport equation, right? There can be some physical models, and all these equations we have to solve, right? So before moving forward in any CFD course, first thing is that we should understand what equations we are trying to solve, right? So in this session or in this week, basically we have covered the governing equations, right? So we will try to solve some problems that those problems will be related to those governing equations. And I will request that if you have any problems in fundamentals of fluid mechanics or basics, then please ask your doubts here or please refer any good textbook for the fluid mechanics. Okay. Okay. So we will begin our session with question number 1. Okay. So here is our first question. Question number 1. It says that an aircraft flies at a constant speed regardless of altitude. With an increase in altitude, its Mach number will. So we have four options. Will it increase, or Mach number will decrease, or will it remain constant? Or we cannot decide based on this given information. So I think this is a very easy question because this has already been discussed in the lectures. So If anyone of you can answer in the comment section, or you can unmute yourself and tell the answer. It is given that speed is constant. Okay, so u, it is constant at all the altitudes. Okay, so u0, let us say at first altitude, and at uh, another altitude is equal to u1, then it is given that u0 is equal to u1. Or altitude is basically height. Okay, height from the sea level. Okay, so at altitude h1, speed is u1, and at h2, speed is equal to u2, and it is given that u1 is equal to u2. We have to tell whether this Mach number will increase or decrease. And how do we define the Mach number? Mach number is defined as speed of flow divided by the speed of sound. Okay, so it is the ratio of flow speed and sound speed. So speed of sound also changes with the altitude, right? Because the properties of medium is basically air. So properties of air changes as the altitude changes. Okay, so the speed of air also changes. Okay, so at altitude h1, let us say speed of air is a1, and at h2 it is a2. So Mach number you can write as u1 by a1, and 2 is equal to u2 by a2. u1 and u2 both are same. So basically question is asking whether the speed of sound will increase or decrease. I think this is a very easy question and all of you can answer. Speed of sound, you can write it as a is equal to under root gamma RT. Okay. Gamma, it is the constant, right? Cp by Cv. R again, it will remain constant for there. And temperature. So whether temperature will increase or decrease. So you know that as you go upwards, as the altitude increases, temperature decreases, right? So if the temperature is decreasing, then speed of sound will also decrease. Okay. So as you go higher, okay, then speed of sound decreases. And since the speed of aircraft is constant and the speed of sound is decreasing, so the Mach number should increase, right? M2 should be greater than M1 if you go upward. Okay. If the altitude increases, then Mach number will also increase if the aircraft flies at constant speed. Okay. I think there should be no doubt in this question. So if there is no doubt, then we can move to question number 2. Okay. Question number 2. It is given that an aircraft flies at a constant Mach number. Okay. So in this question number, Mach number is constant, irrespective of its altitude. Okay. So even if the altitude is changing, the Mach number will not change. It will remain constant. It is given. Okay. At sea level conditions, it flies at 162 kilometer faster than that and at then that and at an altitude of 11 kilometer. Okay. The temperature at sea level is 15 degrees Celsius and its lapse rate in the atmosphere is 6.5 degrees Celsius per kilometer. And it is asking whether the Mach number of aircraft will, what will be the Mach number of aircraft? Okay. So in this question, Mach number is constant, right? So at H1, at altitude H1, the Mach number is M1, let us say. Okay. So it will be U1 by A1. And at H2, Mach number will be M2, and this will be equal to U2 by A2. Okay. And let us say sea level is our H1. Okay. This is our sea level. And Mach number is constant irrespective of altitude. So M1 is equal to M2. This is given. What else is given? It is also given that at sea level conditions, it flies 162 kilometers faster as compared to higher altitude. Okay. This is at altitude equal to 11 kilometers. So it is given that at sea level, it flies faster. Okay. So U1 is equal to U2 plus 162 kilometer per hour. Okay. And if you are writing everything in SI units, then you can convert this thing as well in the SI units. So it will be U1 equal to U2 plus 162 times 3600 divided by 1000 meter per second. Okay. So U2 plus how much? 45. Okay. It will come 45, I think. Maybe you can cross check how it comes. Sorry. Okay. 162 times 3600 divided by 1000. Oh, sorry. We have made a mistake. It should not be 3600 by 1000. It should be upside down. Okay. It should be 1000 times 3600. Okay. We are converting from kilometer per hour to meter per second. Okay. So it should be 1000 divided by 3600. Okay. And speed of sound, you can write in terms of temperature. So A1, you can write it as under root gamma RT1, and A2, you can write as under root gamma RT2. Okay. And T2 will be equal to how much? T1 minus temperature is decreasing at the rate of 6.5 degree per Celsius per kilometer. Okay. So T1 minus 6.5 times how many kilometers? 11 kilometers. Okay. Degree Celsius. Okay. Or if it is in Kelvin, then it will be in Kelvin. Okay. And T1, it is given as how much? Temperature at sea level. The temperature at sea level is 15 degrees Celsius. So T1 is equal to 15 degrees Celsius. You can write this in Kelvin. It will be 273 plus 15. 288 Kelvin. So T2 will be equal to 288 minus 6.5 times 11. So will be how much? Is 71.5. Okay. So 288 minus 71.5, it comes out to be 216.5 Kelvin. Okay. So now you have temperatures. So you can write down the speed of sound. Okay. And Mach numbers are equal at both the altitudes. So you can write it as M1 equal to M2. That gives us U1 by root gamma RT1 is equal to U2 by gamma RT2. Okay. The gamma and R you can cancel out. Okay. So this gamma and R you can cancel out. So what we have? We have U1 and U1 you can write in terms of U2. So U1 is equal to U2 plus 45 divided by root T1. How much is T1? 288 Kelvin. Okay. Equal to U2 by how much is T2? T2 is 216.5. Okay. 216.5 Kelvin. Okay. So now you can solve this equation. Okay. So it will be U2 plus 45 is equal to U2 under root 288.216.5. Okay. So you can write it as U2 1 minus this quantity is how much? Let us calculate this. Under root 288 divided by 216.5. 1.153 minus 1 is equal to 45. Okay. So your U2 will be equal to 45 divided by 0.153. Okay. 0. Sorry. 45 divided by 0.153. It is approximately 294.12 meter per second. Okay. So this is the speed of aircraft at altitude of 11 kilometer. Okay. And you can calculate the speed at sea level as well. Okay. But what we have to find? We have to find the Mach number. Okay. So for Mach number is constant. M1 is equal to M2. So Mach number will be equal to U2 by speed of sound A2. Right. So 294.12 under root gamma R T2. 294.12 divided by gamma. How much is gamma for air? It is 1.4. And specific gas constant for air, it is approximately 287. Okay. Divided by 216.5. Okay. I think you remember this thing, right? Specific gas constant R is equal to universal gas constant divided by molar mass, right? Molar mass. So universal gas constant, you know, it is 8.314, and you have to divide by molar mass. So you'll get this 287. Okay. So if you calculate this quantity, then it comes out to be 294.1 0.12 divided by square root of 1.4 times 287 times 216.5. Okay, so it is approximately how much? Mach number is 0.997 something. Okay, so this is the Mach number. Okay, so that this is what is asked in the question. We have to find the Mach number, and Mach number is coming out approximately 0.997. So if there is any option, well, the closest option is second option, right? 0.995. Okay. Again, very easy question. Just you have to recall these relations. Okay. And while putting the values of any quantity, you have to be very careful. Okay. Everything you should try to put in SI units. If it is not in SI unit, then you should be careful what units you are using. And this R, it is not the universal gas constant. It is a specific gas constant, and it is a specific gas constant for air in this case. Okay. And you know that a specific gas constant is universal gas constant divided by molar mass. Okay. So is there any doubt? Okay, I think it is clear, right? Okay. So if there is no doubt, then we can move to question number 3. Question number 3, it says that the Stokes hypothesis is a simplification used in analyzing Newtonian fluids. Which statement best describes the Stokes hypothesis? So again, this has been discussed in the lecture, right? There is an assumption called Stokes hypothesis. We assume that fluid is following the Stokes hypothesis, and using this assumption, we just simplify the Navier-Stokes equations. Okay. Okay. So what is that hypothesis? What is that assumption? Hello. Okay. So this has been discussed in the lecture, that Stokes hypothesis basically says that the bulk viscosity of a Newtonian fluid can be set to 0. Okay. The bulk viscosity of a Newtonian fluid can be set to 0. Bulk viscosity is lambda plus 2 by 3 mu, and this can be approximated to be 0. This is our Stokes hypothesis. Okay. So lambda is equal to minus 2 by 3 mu. Okay, so this is Stokes hypothesis. So there are most of the fluids that is of our interest. We can assume that those fluids follow the Stokes hypothesis, and those fluids are called Stokesian fluids. Okay. So in this way, we simplify the Navier-Stokes equations. Okay. And one interesting thing is that for incompressible flows, for incompressible flows, we don't even require the Stokes hypothesis, right? Because in that case, Pm will be equal to P. Okay. If there is any doubt or if you want any discussion on this, then please ask. Okay, I think there is no doubt and it is clear. And one thing you should note here is that it is a Stokes hypothesis. Okay, hypothesis means that there can be some fluids for which this hypothesis may not be valid. Okay, there can be some fluids for which this hypothesis cannot be valid. Okay, there if the changes in the flows are very fast. Okay, and the relaxation time required is not met, in that case this hypothesis may not be valid. Okay, so how this what are the physical intuition behind this hypothesis, when this can be valid, when this cannot be valid? So those things I will encourage you to go through, though it is not explicitly related to this course, but just for your interest you can explore. But for the time being, I think you can easily answer this question. Which statement best describes the Stokes hypothesis? Four options are there. First option states that shear viscosity of a Newtonian fluid is zero. So yes, it is incorrect, right? Stokes hypothesis does not say anything like that. Okay. Second option says that Stokes hypothesis states that bulk viscosity of a Newtonian fluid can be neglected for many flows. And third option says it eliminates the need to consider the compressibility of the fluid. So again, this is not correct. Okay. If the flow is incompressible, then you don't even need this hypothesis. Okay. Fourth option says it only applies to turbulent flows, not the laminar flows. Again, this is not correct. So only second option, that it states that the bulk viscosity of a Newtonian fluid can be neglected for many flows. This statement is the best description of the Stokes hypothesis. Okay. I think it is clear, and we can move to the next question. Question number 4. Question number 4 says, in fluid dynamics, what term describes the region of a flow where deviatoric stresses dominate over hydrostatic pressure? Okay, leading to high non-linear behavior and the formation of vortices. So again, there are four terms, four options. So please think and try to answer. Hello. Okay. So this debitoric stresses, stresses and hydrostatic pressure, this has been discussed in the lecture. So if you have not gone through that, please go through the lectures. If you have any doubt, then please ask. Okay. Uh, we will try to solve. I will try to, repeat it for your revision. Maybe you can divide your velocity gradient tensor in two parts, right? Your velocity gradient tensor tau, this you can decompose in two parts. Okay. One part is called hydrostatic and another one is called debitoric. Okay. So this debitoric basically means something related to deformation. Okay. So this is something related to deformation. Okay. Rate of deformation. Is it clear? I hope it is clear. This debitoric basically, this can be written uh, in terms of velocity gradients like del u by del x. Both will have same indices, and the another part where there will be, different indices, uxj plus uxj by del x I. Okay. This part, it is the shear deformation. Someone is trying to learn. Hello. Okay. So the deformation have two parts. One is called shear deformation, and another one is uh, symmetric deformation, or you can say volumetric deformation. Okay. So this lambda, this is called this is something like viscosity, but not that shear type of viscosity. Okay. So this you can say second viscosity or second coefficient of viscosity, and this basically relates this volumetric deformation rate to the stress. Okay. So this basically establishes a linear relationship between stress and this volumetric deformation. Okay. So this is the same lambda that we were discussing in the previous question. Okay. So the deformation, again, I will repeat, this deformation can be divided in two parts. One is a volumetric deformation and another one is the shear deformation. Okay. So in volumetric deformation, the shape will remain same. Okay. The cube will remain same cube. Okay. The cuboid will remain the same cuboid. Okay. The shape will not change, but their volume can change. Okay. It can contract or it can, expand, but the shape will not change. Okay. So that deformation is our basically volumetric deformation. And another one in which the shape will change, the shear will come into the picture. That is shear deformation. Okay. So this is the debitoric part. And hydrostatic pressure, you already know, right? Hydrostatic uh, thing, you know, right? In the question, it is saying what term describes the region of flow where debitoric stresses dominate over hydrostatic pressure. Okay, so it is saying that this debitoric uh, pressure is dominates over this hydrostatic pressure. So what is that region? And in that region, it is saying that that is the region of highly non-linearity. Okay, high non-linear behavior and the formation of vortices. What is that region? That is the shear region, right? There will be a lot of deformation. Okay, and deformation we have already discussed. It is related to debitoric term, not the hydrostatic term. Okay. I think it is clear, right? The correct answer will be shear layer. If any doubt, then please ask, or you can write in the chat box. If there is no doubt, then we can move to the next question. Okay, so we will move to the next question, question number 5. In question number 5, there is equation. So P by dot T plus dou by dou Xi of rho Ui is equal to 0. So this equation represents the differential form of which conservation equation? Is it mass conservation or momentum conservation or energy equation of energy equation, or it is the equation of state? So this is, I think, the very trivial question, right? Every time we are using this.
So mass conservation.
Yes, it is mass conservation. So you can easily drive this equation. You can just assume a small elemental volume. You can assume assume the density to be rho, and you can write dm by dt is equal to 0. Okay, and you can arrive to this point. Okay, so if you have any doubt and if you want more discussion on this, then we can go ahead. Or I think it is very trivial. It has been discussed in lecture or maybe in fluid mechanics course. You should know this. So is there any doubt in this question in any term or whatever? Sometimes you may find that gradient of velocity is equal to 0. So is this equation, first equation and second equation, are both of these same or two different equations? So is the second equation also the mass conservation equation? I mean, in a general sense. Which one is mass conservation equation? Equation 1 or equation 2? Okay, I am just asking that divergence of velocity is equal to 0. So what does this mean? If someone is saying that divergence of velocity is equal to 0, or anywhere you find this relation divergence of velocity is equal to 0, then what does this mean?
So incompressible flow.
Yes, it means incompressible flows. Okay. So this divergence of velocity is equal to 0. This is not the general mass conservation equation. This first equation, that is del by del t of rho plus del by del xi of rho ui is equal to 0. This is the general differential form of mass conservation equation. And second equation, that is divergence of velocity is equal to 0. This simply means that flow is incompressible. Okay. Okay. So I think it is clear. And this is divergence, and sometimes you may encounter with curl of velocity is equal to 0. So what does this? What is this? So first equation was our mass conservation equation. Second equation basically means your flow is incompressible. And if you find that curl of velocity is equal to 0, then what is this?
Irrotation.
Flow is
Irrotation.
irrotation. Yes. So all these small things should be clear. If you have any doubt, then please ask, or please refer to any uh, textbook of fluid mechanics, because all these small concepts will be encountered very frequently when you move ahead in the CFD course. Okay. Okay. So I think this is very, trivial. And if there is any doubt, then please ask, or we can move to the next question, question number 6. I think it is clear, right? Okay. We can move to the next question, question number 6. Question number 6 says, for the flows with shocks, which of the following form of equation is more suitable? Conservation form or non-conservation form or primitive form? So any of you can please answer. Which option is the correct one? You know the difference in conservative form and non-conservative form, right? So conservative forms are those which are directly derived from the conservative laws. Okay, the control volume conservation consideration. If you apply, then whatever equations you are getting, those equations are conservative form. Okay, and you just simplify them more, then you get little simpler version of those equations, and they are non-conservative. Okay, so non-conservative equations are simpler, right, to write and understand. But if the flow has any discontinuity or sudden changes, then that form is not suitable. Okay. So in CFD, many times you do simulations involving the shocks, okay, shock waves. And in shock waves, you see there are sudden changes or discontinuities. Okay. So non-conservative form will not help you there. Okay. Then you should go for conservative form. Okay. So conservative form is more suitable for the flows which involves the shocks. Okay. So probably this would have been discussed in the lecture. Maybe I can write both the forms for maybe momentum equation. Okay. So conservative form of momentum equation is, first there will be temporal term, right? So dou by dou t of rho ui plus, then there will be convective term, right? Dou by dou x j of rho uj ui. Okay. Then on the right hand side, what you have? You have the pressure gradient term. Okay. So del p by del x with a negative sign, del x j. Okay, we are writing, sorry, I in ith direction we are writing, plus del by del x j of, what is the second term? Viscous term, right? The shear stress term. Okay, so here you have to write the shear strain u I by u j, sorry, x j. Okay. Then there is another, that bulk viscosity term, right? Of what was that? Lambda plus mu del by del x, uh, same, and this is k. Okay. So pressure term, viscous term, bulk viscosity, and maybe some body force term, rho g or whatever. Okay. So this is conservative form, and non-conservative form you already know. So this is non-conservative form. How do you derive the non-conservative form? You just expand this term, okay, using the chain rule. Then you use the mass conservation. Okay, you will just subtract the mass conservation equation after expanding this term. Okay, so you will have the simpler version. Okay, the simpler version is basically rho, and the total derivative will be there by dt of ui plus, sorry, now the total derivative, you know what is total derivative? Total derivative is rho plus, what is that next term? You know total derivative? In the first question we have written. Okay, anyways. So total derivative is, I can write it here. So dy dt is of any quantities like this, plus of that term, of that term. Okay, so this is total derivative. Okay, so this is what we mean by capital D by capital T. Sorry, capital D by capital dt. So this is total derivative. So this is equal to pressure gradient plus again this shear stress term L by del x J of what shear stress, what will be the I and J, and viscosity coefficient plus del by del x J of lambda plus u. Okay. Plus OGI. Okay. So right hand side you can see it is exactly same, but only the left hand side is different. What is the difference? Here inside the bracket there is rho. Okay. So sometimes what students do, they just bring this rho out as if it is constant, but that is not the correct way. Okay, you cannot simply bring this rho outside, right? So you have to apply the chain rule, and after the chain rule, you will get this term, this term. Okay, then this term will be set to equal to 0, and then left hand side will be uh, reduced to this total derivative. This total derivative. Okay, this is total derivative. Someone is trying to join.
Already
Huh? Hello.
Who is not update in the sheet. அப்பனா என்ன அர்த்தம்?
I think who is talking? I should mute.
அவங்கள எல்லாரும் யாரு நோட் பண்ண?
Okay, sorry. Okay, I will just summarize what I have done. Okay, this is the conservative form. This is the conservative form. So this equation is directly derived from the control volume using the conservation concepts. Okay, and the left hand side can be extended using the chain rule, and in that after expansion you will get this term, and plus something else. So this term will be set to equal to 0 from the mass conservation, and the remaining term will be this one. Okay, this one. This is called total derivative. Okay, so total derivative of velocity. Okay, so this big equation, not big equation, just similar equation. This will be simplified to the this non-conservative form. Okay, but this non-conservative form, this looks simpler, but for flows which have some sudden changes or discontinuities, this is problematic. Okay, why this is problematic, that we will discuss when we discuss the shocks and compressible flows. But for the time being, you should understand that this non-conservative form, it's sometimes called weak form, and the conservative forms of equations, that is called strong form, because strong form means it can deal with discontinuities as well. Okay, so coming back to the question number question says the flows with shocks which type of the following form of equation is suitable. So conservative form is suitable because it can deal with the discontinuities or sudden changes. Okay, so if there is any doubt, basically few terms which you should know is that what is total derivative, how to do this expansion using chain rule, and how to make this term 0. This is basically mass conservation, and you get the non-conservative form. Okay, so if there is any doubt, then please ask, or you can just revise using any fluid mechanics. Next. Question number 7. Question number 7 says which parameter in the fluid dynamics characterizes the ratio of kinetic energy to the internal energy in a gas flow. So again, we have 4 options. Reynolds number, you know Reynolds number. What is Reynolds number? Reynolds number is basically the ratio of inertial forces to the viscous forces. Okay, it is not the ratio of kinetic energy to internal energy. So this is not the correct option. Mach number, Mach number is the ratio of uh, speed of flow to the speed of sound in the medium. So whether it is related to kinetic energy and internal energy, that we will come back. And Prandtl number, it is something related to heat transfer. Okay. You know what is Prandtl number? Prandtl number, Grashof number from heat transfer background. These non-dimensional numbers are very important. Why? Because whenever you have the equation, for example, this Navier-Stokes equation or the momentum conservation equation in any form, okay. So what we do before doing further analysis, we non-dimensionalize these equations, okay. And when you non-dimensionalize any equation, you get some non-dimensional numbers, okay. For example, if you non-dimensionalize this Navier-Stokes equation, you will get 1 by Re in the equation in the non-dimensional form. That same Re, the same Reynolds number, okay. Okay, so you will get some non-dimensional numbers when you non-dimensionalize your governing equations. So what is the meaning of those non-dimensional numbers? What will happen to the physics if these non-dimensional numbers are changed in magnitude? For example, high Reynolds number and low Reynolds number. So what will be the difference? You can easily tell that for a high Reynolds number, you can ignore the viscous effects, right? Not always, but that's what it means, right? High Reynolds number mean. Okay, the Mach number, it is equal to speed of flow to the speed of sound. Okay, so speed of sound, it is gamma RT, and this U, it is the speed of flow. Okay, and this temperature is directly related to internal energy. Okay, for ideal gases, this internal energy is the only function of temperature, right? So it is related to internal energy. And it is related to speed. So it is directly related to the kinetic energy. So Mach number is the correct option. Second option is the correct option. Okay. So if there is any doubt, then please ask. Or if there is no doubt, then we can move to the next question. Question number 8. It says that Bernoulli equation is applicable for incompressible flows, incompressible viscous flows, and last option says inviscid incompressible flow. So very easy question. Any one of you can please answer. What should be the correct option? Is Bernoulli equation applicable in viscous flows? It is very important to know which equation is applicable in what conditions. Okay, you cannot apply every equation everywhere. Okay, before applying any equation, you should understand whether this equation is even suitable in that condition or not. Some equations, for example, if any equation is related to momentum conservation and you are dealing with a situation when momentum is not conserved, then you cannot apply that equation, right?
So fourth option, sir. Invested and income results.
Yes, exactly. The fourth option is the correct option. Why? Because Bernoulli equation, when you derive, it is some sort of energy balance, right? Kinetic energy plus potential energy plus pressure energy. Okay, that total sum remains constant. So if there is a source of energy generation or a sink where energy is being dissipated, then this energy will not remain constant, right? Kinetic energy plus potential energy plus pressure energy, this total sum will not remain constant. Okay, so in viscous flows, there are viscous dissipations. The energy is dissipated into heat, right? So you cannot apply the Bernoulli equation there. Why? Because Bernoulli equation is the conservation of these terms, mechanical energy, sorry, kinetic energy plus potential energy plus this pressure energy. So it is not applicable when the viscosity is dominating. And it is also not applicable for compressible flows. So it is applicable when the flow is incompressible and inviscid. Fourth option. Okay. Okay. Question number 9, it is related to TDS relation. It is given that TDS is equal to CV dt plus PdV. And it is asking when this is valid. So again, the similar question, by similar, what I mean is that when this equation applicable. In the previous equation, it was asked about the applicability of Bernoulli equation. Now the applicability of this TDS relation. When this is applicable. You can grab this equation from first law of thermodynamics. It is just energy conservation, right? First law says that heat that you are providing to a system, okay, D, that will either increase the internal energy dE plus, or it will do some work. Okay, this is the first law of thermodynamics. Then if you assume simple compressible system, reversible one, then you can write dq is equal to TE plus PdV. Okay, so this PdV is applicable only for these simple compressible reversible systems. Okay, del Q is equal to TdS for reversible systems. So for reversible systems, you can write TdS is equal to TE plus PdV. And dE you can write in terms of temperature. So TdS is equal to CV dt plus PdV. Okay, so we have derived this equation from the first law of thermodynamics, but using some assumptions. So first we assume the system is simple compressible and reversible Then the second step also we assume that system should be reversible. Then we arrive to this final form. So now if I ask that this TdS is equal to CV plus dt plus PdV, it is valid for reversible or irreversible or both reversible or irreversible, or it is incorrect. So it is not incorrect. You must have guessed that, right? We have derived it correctly, so it is not incorrect. So now you have to just answer whether it is applicable for reversible one or irreversible or for both.
Only reversible.
Only
Reversible, sir. Reversible.
you mean first option, right? Okay. So here is the interesting point that I want to put. Even though while driving this equation, in both steps we have assumed that the process should be reversible here as well in here. But this equation for valid for reversible as well as irreversible processes. Now you have to tell why. It is valid for irreversible process as well. Can you tell why? Even though we have taken these assumptions. We have derived this equation for reversible systems only, but it is valid for reversible as well as irreversible.
Internal energy is there.
Internal energy is there. So
It is a point function actually.
okay, internal energy is point function. Actually, all of these terms involving in the final form are point functions. Okay. Temperature, it is a point function. Entropy is a point function. Pressure is a point function. Volume is a point function. So all of these are point functions. These point functions, what are the point functions? Point functions does not depend on the path. Okay, these are the point functions. They are just uh, properties of a point. Okay, they are just the thermodynamic signature of a system. Okay.
Okay.
So whether the process is reversible or irreversible, that is path dependent. Okay. So how you are moving from one point to another point in a thermodynamic sense. But these point functions, they don't depend on the path. Okay. Pressure at one point is the pressure at that point. Okay. How do you reach that point does not matter. Okay. So the properties involved in the final equation, they all are the point functions. So it does not depend on the path. It does not depend on the process. So it is applicable for reversible as well as irreversible. So this is the power of this equation. Okay. The first two equations, for example, this equation involving dq is equal to something, or this equation, for example, dq is equal to tds. You cannot apply this equation everywhere, right? You cannot apply this equation when there is some entropy generation due to irreversibilities. But the final equation you can apply anywhere. So this is even more useful. Okay. But anyways, I think for the question point of view, you can easily answer that correct option should be third option. Why? Because all of these are point functions, not dependent on path or process. Okay. So I think it is clear and we can move ahead. Next question, question number 10. Question number 10 says, for which type of the substances are the equations of state typically more complex, requiring consideration of constant volume? Ideal gases? No, for ideal gases, equation of state is really simple, right? Ideal gas equation. Real gases, again, there is little modification in the gas equation, but real gas equation is also not very complex. Okay. There are a few additional terms. For example, van der Waals gas equation, but it is not very complex. Solids and liquids. Solids, for solids, the volume is constant, right? So volume is constant and other things, they are more or less constant. But for liquids, these equations, equation of state, they are typically more complex, and we have to take some assumptions. Okay. So for writing the equation of state for liquids, we need to make some assumptions. For example, considering the constant volume. Okay. So the correct option is fourth one. Okay. Now question number 11 says, what is the total number of independent terms in the Reynolds stress tensor for a three-dimensional turbulent flow field?
Six.
6, yes. For a three-dimensional flow field, there are 6 independent terms. Why? You know what is the Reynolds stress term? Reynolds, maybe when we study the runs, then probably we will discuss. But just to give you an idea, we have the Navier-Stokes equation. We average that equation in a very special manner. Okay, some terms cancels out. Okay, they become 0, and there is some additional term. Okay, and that additional term is basically Reynolds stress term. Okay, when we will discuss this runs, then we will go in more detail. But it involves the fluctuating components. Okay, for example, ui, uj, the fluctuations of these components, and average of this. Okay, the average of the fluctuating components. Okay, so if you write it is in the matrix form, it will be uii, uj, sorry, 11, u11, u22, not 22, u2, u3, u3, and similarly u1, u2, u1, u3, u2, u1, u2, u3, and u3, u1, u3, u2, and not u1, but their fluctuating component. Okay, for fluctuating, sometimes we put these small bar, these small primes. Okay, now this is just the product. Okay, for example, if you take this term and this term, both of these are equal, right? It is basically 2 is equal to 3 is equal to 3 is equal to 2. Okay. So how many independent terms are there? This is independent, this is independent, this is independent, and this is independent, this is independent, this is independent. Okay. And these remaining three terms, so these are equal to these three terms. Sorry, these three terms. So how many independents are there? 1, 2, 3. Sorry, 4, 5, 6. So these 6 terms are independent. Okay. Okay. So I think this is clear, right? If there is any doubt, then please ask, or we can move to the question number 12. Is it clear? So if you have any doubt what is RANS, basically it stands for Reynolds Averaged Navier-Stokes equations. And what we basically do, we decompose any field in uh, into the mean flow and the fluctuating, I mean the mean component and the fluctuating component. Okay. Then we do averaging. Okay. Then we do averaging. And using some simplifications, we arrive at RANS equations. And in that, in those RANS equations, there is a additional term, and that additional term is this, and this is called Reynolds Reynolds stress tensor. Okay, when we discuss this RANS, then we will go in more detail. But anyways, so for the time being, six components, sorry, six independent terms are there. Okay. So question number 12 says Euler's equation can be used to solve. Question number 12 says Euler's equation can be used to solve potential flow, boundary layer flow, inviscid flow, or viscous flow. So Euler equation, again, the same energy conservation. You
Non-viscous.
drive the Bernoulli
Inviscid flow.
equation. Huh?
Third option. Okay.
And what about potential flow? You know what is potential flow? So
Maybe delta dot U equal to 0. Not sure of it.
maybe what? Irrotational flows. Okay. So for irrotational flows, you can define a function called potential, right? Such that the gradient of that potential gives you the velocity field. Okay. So this potential is basically a scalar. And when you take the gradient of that potential, you will get the velocity field. This potential can be written for any irrotational field. Okay. For example, in your electrodynamics, you have studied the electric potential. What is the gradient of electric potential? That is electric field, right? And you know, electric field is irrotational field, right? If you write the curl of electric field, it will come out to be 0. In most of the cases, not always, right? Not always. At least for electrostatics, it is correct. Anyways, coming back to fluid mechanics, again, I will repeat. When the curl of a field is 0, then you can define a scalar called potential such that the gradient of that scalar will give you that field. Okay. For example, if you talk about velocity, if the velocity is irrotational, if the velocity field is irrotational, that means the curl of velocity is 0. So in that case, you define a function called potential function such that the gradient of the potential function will give you the velocity. Now, what are these curl, divergence, gradients? That should be clear. If it is not clear, then please ask here. I can explain it. And if you know, then we can move ahead. So someone answered that it is valid for inviscid flow. Yes, it is valid for inviscid flow and for potential flow. So both options are correct. It is not valid for viscous flows. Okay. And boundary layer flows, obviously not correct. Why? Because boundary layer are the reason where the viscous forces are significant. Okay. And when the viscous forces are significant, you cannot use the Euler equation. So potential I can tell quickly. So if you have this phi, scalar phi, then you take the partial derivative of phi with respect to x. This will be your x component. If you take the derivative of this phi with respect to y, it will be your y component. If you take the derivative with respect to z, it will be your z component, and this will be your velocity vector. So this phi you can define every time when the curl is 0. Okay, so this is irrotational. And if the divergence is 0, then it means flow is incompressible. Okay, so this is called gradient. This is called gradient. So gradient of potential or velocity potential, let us write, of velocity potential is equal to velocity field. Okay. Phi can be defined when curl is 0 or flow is rotational. Okay. So potential flows involve this scalar phi, and analysis involving the scalars are relatively simpler. Okay. So there are a lot of problems which can be solved easily if they can assume to be irrotational. Okay. So if a flow is